finite point sets are closed. Closed. Note, we've shown Hausdorff implies T1. T1. In fact, T1 is weaker. It's a weaker assumption. Yes, a weaker assumption. Weaker assumption than Hausdorff. Let X be a space satisfying T1. Where X is space satisfying. Then A and let A be a subset of X. Then X is a limit point of A if and only if every neighborhood of X contains infinitely many points of A. X is a limit point of X. X is a limit point of X if and only if for every neighborhood of X contains infinitely many elements. Sure. No. I don't know. Sure. I don't care. Me. Here. Then no, infinitely many. Yeah, okay, infinitely many points of A. Okay. Let X satisfy T1, then for every neighborhood of X, the neighborhood contains infinitely many points of A. Why? Suppose. Why? Whatever. Do one by one. Suppose X is a limit point of A. What does that mean? Then that means that for all U in neighborhood of X, we have that U and A remove X is non-empty. Am I stupid? Okay. If for every neighborhood of X, we have U intersect A at infinitely many places, then consider U and U is equal to infinity. Okay, so you intersect in that many places, and in particular, u and e not in X is not empty. It's not empty, so X is a limit point. Okay. Now this way, if X is a limit point of A, then what? Okay, I think it's contraposition. No, is it? Am I stupid? Am I stupid? No, it's like fucking contradiction, I think. I suppose. Oh, okay. Suppose. Suppose there exists u neighborhood of X where u intersects A at finitely many points. So u is closed. Because it's a finite set. U is closed in A. U is closed in A. Wait, U is closed. Am I stupid? U and Y is closed. Okay, U closed in Y means U and Y. U and Y. But and then okay, then want to show that X is not a limit point, right? But U is open. What do you do next? Then U intersect with A, remove X is also finite, and so U intersect A, remove X is closed. Let U be a neighborhood of X where, and then okay, what? U intersects A. U intersect A. Okay. So we say this is equal to x1 to xn. This is closed, so X remove these finitely many points is open. And then what? X is in that. Now, x is in this, is in x, remove this. So this thing is in the neighborhood of x, but this thing, u and a, oh, x remove u and a is and a is what? It's not empty? Is it not empty? X remove u. X remove the things in u. X remove the things in u and a, but then you add that x. That's crazy. What the hell? Is you want a contradiction? What? Am I stupid? The intersects the a not at all. What is? Okay. If we have T1, then you are a limit point if and only if for every neighborhood the neighborhood intersects A at infinitely many points. And the proof is that if for neighborhoods you have an intersection that's infinite, then you remove x, okay, whatever. That's the easy bit. If you, by contradiction, suppose for contradiction that there exists some open set, some neighborhood where you have finite intersection. We have finite intersection. If we have some neighborhood, okay, if we have a limit point with neighborhood with finite intersection, then what do you have? Because it's T1, a finite intersection means the intersection is closed. But since this is closed, no, we don't care about this. We don't even care about this because we care about this. We care about this. So we can okay. We need this, but only just like very in passing. We need this to get to this. It's just one step. So this, the intersection of this intersection is like finite, so it's closed. And because it's closed, the complement is open. So we want to show that this is a neighborhood of X with finite intersection. Wait, what? No, we want to show that, okay, because it's a limit point of, this means that for every, okay, This means that for every u in for every u for every neighborhood of x, we have that u and a is non-empty. So we want to find some for contradiction. Find some u neighborhood of x with empty intersection. And the claim is that this open set right here is a neighborhood of x with empty intersection. So why? Okay, so you explicitly remove x. X is not here. X is not here. So x is here, x is in here. So this is open, which contains x, is a neighborhood of x. But how do you know this is empty? Because we have the n. What? We have. You have okay. Why? Because if something in here, why is this empty? Let's do. Something is in here. Why is this empty? Q and A remove. Oh, okay. It's X remove U and U and let's try U and A remove X. U and A remove X and A remove X. What? Am I stupid? X and U. Yeah. Turn on if Y. So, then Y X. Am I stupid? Oh, there we go. If something is in here, if something is in here, then it is not in A remove X. If something is in here, then it is not in U and A remove X. So it is not in A remove X. Okay, yeah. If not in U and A. Sure. Okay. Okay, there you go. Once experienced with open and closed sets and limit points in the real line and the plane can be misleading when one considers each point set is closed. This fact is easily proved. Each point is blah, blah, blah. Similarly, once experienced convergent properties in R, also can be misleading when used general topological spaces. In an arbitrary topological space, once is a sequence of x1 and x2 points in a space, x converges to the point x of x, provided that corresponding to each neighborhood u of x, there exists a positive integer n such that xn is equal to blah 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 blah. Hausdorff. If X is a Hausdorff space, a sequence of points converges to at most one point of X. It means that converges to if converge again. then a sequence of points converges x in all points. Why is that the case? What color am I missing? Am I stupid? No. Yes. Yes, I am quite stupid. Oh, that's a surprise. You know? I'm not really smart. Okay. Limits. Why? What does it mean to converge? It means that if for all we have xn converges to x if for all n if I don't know if for all n that exists u in the neighborhood of x such that u for all I think this makes sense. I don't think they mention it anywhere. They mention it anywhere? No way you don't mention it anywhere. No way you don't mention it anywhere. What is it? Sure. This works. Why not? Why doesn't it work? It works. It should work. Why would it not work? Right, so it works. It works because there's no chance it doesn't not it there's no chance it does not work. Yeah? Okay. Do I do contradiction? What do they do? What do they do? Oh, okay. So, what they do is you let the sequence converge to a point and then show that no other point can be the limit of the sequence. Proof. Suppose xn converges to x, i.e. and let y be an element of x which y is not equal to x. Then, since it's Hausdorff, my Hausdorff property, Hausdorff, there exists u, let's say, okay, u1 in the neighborhood of x and u2 in the neighborhood of y Oh, let's not use u2. Let's use v in the neighborhood of y, such that what do you have? We have u and v are disjoint. Then now what? Since it converges, then u is this here? But no. I'm stupid now, what to do? Whatever. U and V are disjoint neighborhoods of what? Since U contains xn for all but finitely many values of n, what? Oh, I'm actually stupid. If for all U in this that exists, such that, okay, so here we have U contains all but finitely many xn. So V can only contain finitely many xn. And hence y is not xn does not converge to y. Why? The limit is unique. It's like this. Every simply ordered set is a Hausdorff set in order topology. The product of two Hausdorff spaces is a Hausdorff space. A subspace of a Hausdorff space is a Hausdorff space. If the sequence xn of the points of the Hausdorff what is a toe set? A toe set is a Hausdorff space in a product topology. Blah 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 blah. We shall study a number blah blah blah. The Hausdorff condition is generally considered to be a very mild extra condition to impose on a topological space. Indeed, in a first course in topology, some mathematicians go so far as to impose this condition at the outset, refusing to consider spaces which are not Hausdorff. We shall not go so far, but we shall certainly assume the Hausdorff condition whenever it is needed in the proof without having any qualms about limiting seriously the range of applications of the results. The Hausdorff conditions is one of the number of extra conditions one can impose on a topological space. Each time one imposes such a condition, we can prove stronger theorems, but one limits the class of spaces to which the theorems apply. Much of the research that has been done in topology since the beginning have been centered on the problem of finding blah blah blah. Finding conditions that would be strong enough to enable one to prove blah blah blah, and yet not so strong as the limit is available in the range of applications, which are studied in the Hausdorff condition and so on are but two of a collection of conditions that are similar to one another but are collectively called the separation axioms. Other conditions include the countability axioms, the various compactness and connected conditions. That's crazy. So crazy. So crazy. So crazy. Let X be a toe set. Theorem 1. Let X be a toe set. Let X be a toe set. Then order is Hausdorff. Proof. How do you prove that this is Hausdorff? Proof. Aha. Proof. Let xy in X be distinct. Then the utmost of generality say x is less than y, then what? Consider we have, what could we possibly have? Aha! We could have, if, I don't know, if A not exists, then what's the order topology again? You have order topology means your basis is an open race. No, it's AB, 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 and AB. Okay. Stop. Yeah, exactly. So if A exists, then Y and I don't know, and B exists. Okay, then what do we have? Not including X. This is our this, and this is this. And if the bounds don't exist, if there's no, then can find you know, P, Q, just that, P less than X, or Q greater than Y, and hence we have P, what do you have? P go to Y is in this with Y and X is to, no. Am I stupid? Yeah. Wait. What am I? Oh my god, am I stupid? I'm actually stupid. Oh my god. They need to be. They need to be. They need to be disjoint. They need to be disjoint. So I pick something a little bit greater than. Am I stupid? Every order topology is house-closed. Why? Why? Yeah, that's as close as I can get it to. And then what would be a neighborhood of y? What would be a neighborhood of y? Am I overthinking shit? Oh, but what about shit in between? The problem is things in x and y. The problem is the things in x and y. The problem is that I have intersection of x and y. Can I remove shit from it? How do I remove shit from it? Can we say how about this? What? So, why? Why is it house doors? But they might intersect in xy. Can we remove xy? What about if we think about subbases? Subbases, which is, I don't know, negative to x and then negative to y. and x to this, and y to this. And then we take negative x but then you have here you have the possibility of intersection. And Hausdorff doesn't want you to have that. Hausdorff doesn't want you to have that. Hausdorff doesn't want you to have that. Am I overthinking shit? No way. Uh-huh. Exists. Then if x is empty, then that's then this and this and this what? Or we can just consider subbases. Would it be simpler? Whatever. One. Subbases for my sanity. Subbases. Think. Raise. If this is empty, then negative this to y is the neighborhood of x. This is the neighborhood of y, where this to y and this to this is equal to this, which is equal to empty. If this is not empty, let exactly pick something here and then do this, and then this to this, and this and this to this is equal to empty, and so we have stuff. What else is Hausdorff? The product of two Hausdorff spaces is a Hausdorff theorem. 2. Let x tx and y ty be both spaces. This house door. Proof. Let x1 y1 x2 y2 be in x1 x times y where be distinct. If x1 is not equal to x2, then there exists u1 in the neighborhood of x1, u2 in the neighborhood of x2, such that u1 and u2 are disjoint. Then consider for basis consists of u times v, u times v, where u is x, v is cy. Okay, then consider then we have y1 be neighborhood of y1, y is equal to y, u1 2 in the neighborhood of y1, y2. Consider u1 y, u2 y in basis where what do we have now? We have x1 y1 is in u1 times y, i.e. u1 times y is in the neighborhood of x1 y1 x2 y2 is in u2 times y, so u2 times y is an element of the neighborhood of x1 y1, x2 y2, and u1 plus y and u2 cross y is equal to u1 and u2 cross y is equal to empty. So, okay, now if x1 equals x2, then necessarily y1 is not equal to y2 and do similar. And hence product topology T x and y is Hausdorff. A subspace of a Hausdorff space is a Hausdorff space, blah. And 3. Let x, Tx be Hausdorff. Then topology is also Hausdorff. Proof. Proof that, I don't know, y1, y2 be distinct. Then because it is okay, then there exists u1 in the neighborhood of S is x of y1, u2 in the neighborhood in x of y2 such that u1 and u2 are disjoint. Then u1 it is in u1 and then u2 and y u2 is in the neighborhood y of y2 where u1 and u2 piece of this is the intercept. Show that X is Hausdorff if and only if the diagonal is closed in X. Show that the T1 axiom is equivalent to the condition that for each pair of points X, each has a neighborhood not containing the other. No way! No way! If and only if the diagonal cut rod. Proof. It's not closed. Okay. Why? I don't know. PQ B in so since PQ P is not equal to Q. So PQ is a limit point. We have that for each U in the neighborhood of PQ PQ and this remove PQ is not empty. Okay, now we have to use properties of x cross x. So then, okay, so x is no longer Hausdorff. X is not Hausdorff. So if it were, suppose for contradiction it were, and there exists P into P, Q, R, and S. And there exists P, there exists U1 in the neighborhood of P, U2 in the neighborhood of Q, the U1, U2 disjoint. And then let U be U1 plus U2. Then PQ would be in U, but UN and because if U and this is okay, no, look, if EB is in UN and this, then A equals to B, so A is in U1 plus U2, so U1 and U2 is not empty. Then P and U, and but then U and this, but P and Q, yeah. So and so, U and this is equal to this. U and what's that? This is also is it's also empty. boundary of A is the closure of the intersection of the closure of A and the closure of the complement of A. It means the shit that is bound to be in. Oh, okay. So we have shown that Hausdorff implies a closed. If it's Hausdorff, if closed, is closed, let X, Y, and Z be distinct. Then it's not Hausdorff. Am I stupid? No. If not, okay, there we have if not closed, then something, and then it's Hausdorff. If it's not closed, then we have something, and then it's Hausdorff. Because if it's not, then we have something crazy. If it's not closed, then it's not Hausdorff. Yeah, so we have if it's not closed, then it's not Hausdorff. So Hausdorff implies closed. Now we have if it's closed, then we have Hausdorff. Why? If not Hausdorff, it's not Hausdorff, then there exists I don't know, oh, u1, uv, then uv, u in the neighborhood of x, v in the neighborhood of y, v a neighborhood where u and v are disjoint. No, if it's not Hausdorff, then the existences are not disjoint. No, then for all for all u in the V a neighborhood, we have u and v are not distinct. Then, and then. So, let's try. So consider, I don't know, I don't know, y, no, not y, other z, z in u and v, then z is in u plus v, which is in the topology of this. Okay, and so what? I want to show not i.e. Not i.e. So what? The limit point. The limit point is where for where there is some limit there. That means something there. That's why. Is it considered what do I do now? For every neighborhood. So consider u is in w, I guess. W is in that i.e. This is PQ, into PQ, then expect that such that P is not equal Q, but for all U, for all W in neighborhood of PQ, we have that it's not equal. Yeah, because equals the intersection of some B, some, I don't know, some open sets, I don't know. And then for each thing, the intersection of that is the intersection of U, I, U. So U, V, and U is not empty for any U V for distinct X, Y. Where U R and P, C, J, Q, P, Q, and then it's greater than is not, and so contradiction. So it's not. So IE not closed, and we are done. Whatever.